Hi, this is a video to help you through the activity on representing molecules on paper and the activity on functional groups. Please have your activity in front of you and follow along as we cover this information. Make sure you answer all of the questions as completely as possible and check your key to make sure that you're correct. We're going to start with representing molecules on paper. And we're going to start with isopropyl alcohol and N-butyl alcohol. In front of you on your activity, you should have a figure that looks similar to this slide. What I'm showing you here is 5 different ways that you can represent isopropyl alcohol on a piece of paper. Now, in the last activity, we learned about molecular shape and you built some models. Your models looked like the picture that we're labeling here as the ball and stick model. For isopropyl alcohol, this shows you all of the connectivity of the atoms. The black circles here are carbon atoms, the white circles are hydrogen atoms, and the red circle is an oxygen atom. So this is basically kind of a picture of a ball and stick model, just like the ones that you built in class. And this is one way that you can represent the connectivity between atoms in isopropyl alcohol. So notice here that we have 3 carbons directly attached to each other, and then the middle carbon is attached to an oxygen, and then basically all of the carbons have hydrogens on them so that they have a total of 4 bonds, and the oxygen here is attached to a hydrogen and it has a total of 2 bonds. So the ball and stick model tells you a lot about the shape and the structure, the connectivity of a molecule. So now let's go to the very other extreme and talk about the molecular formula. This is another way to show a molecule or represent a molecule on paper. The molecular formula just simply tells you the number of different types of atoms in the molecule. So look at this molecular formula. There's 3 carbons, 8 hydrogens, and 1 oxygen. It tells you about the types and the number of atoms, but it doesn't tell you anything about the connectivity or how the atoms are connected. The condensed structural formula is kind of like a fancy molecular formula. In the condensed structural formula, there is some information about the connectivity of the atoms. Normally, the carbons are written in the chain, and right behind each carbon are the atoms that it's attached to. So if this carbon here is this carbon, you can tell that it's attached to 3 hydrogens. And then this carbon is attached to this carbon, which is this one. This carbon is attached to a hydrogen, like that, and an oxygen with a hydrogen on it. So that's this thing here. And then that carbon is attached to this carbon, and this carbon here is attached to 3 other hydrogens. So the condensed structural formula tells you the types of atoms and the number of atoms, but it also tells you something about the connectivity. Lewis structures are the things that you're familiar with at this point. So you can draw a Lewis structure for a molecule to represent how the atoms are connected. So this also gives you the same sort of information as the condensed structural formula, but it's more like a picture than just a line of text. So the Lewis structure, one thing about a Lewis structure is that you always have to show the lone pairs of electrons if there are any. So this oxygen here has lone pairs on it. But notice that there are no lone pairs represented on any of the other types of representations. So the Lewis structure is special in that you must show the lone pairs. A skeletal structure is kind of like a Lewis structure, but it's a shorthand. The way that a skeletal structure is drawn is basically, it leaves off all of the carbons and they're assumed. So at the end of every line and at the intersection of any 2 lines or 3 lines or 4 lines, you have to understand that there is a carbon atom. So this skeletal structure here represents this Lewis structure or this ball and stick model. Here's a carbon that's at the end of the line. That would be that carbon. Then there's another carbon up here where the lines are intersecting here. And then there's another carbon down here at the end of the line. There is not a carbon at the end of this line because an oxygen is drawn there. So there's never a carbon at the end of the line if another atom is drawn there. So this here, you see that this is a carbon here, and the line ends at oxygen. So the oxygen is directly attached to the carbon. And then you have the hydrogen as well. Rules about skeletal structures are that you don't draw any of the carbons, and you don't draw any of the hydrogens attached to the carbons. You assume that there are as many hydrogens as you would need to fill the bonding of carbon. And we know that carbon always has 4 bonds. So you see that this carbon here is attached to one other thing, the carbon. And so you have to assume that there are enough hydrogens around that carbon to fill 4 bonds. So if there's 1 bond to carbon, then there have to be 3 hydrogens attached here. Think to yourself what this carbon is bonded to and how many hydrogens it would need to make 4 bonds. Notice that this carbon is attached to the oxygen, it's attached to this carbon, and it's attached to this carbon over here. So that's 3 bonds that are drawn, and then it would need 1 more bond, a hydrogen. So there's a hydrogen here on that carbon, and you can see that from this ball and stick model. So you never draw the hydrogens that are attached to the carbons, and you never draw the symbol for carbon, but you do always draw the hydrogens attached to oxygens and nitrogens and other atoms. For skeletal structures, you don't have to draw the lone pairs, but I recommend that you do draw them, just to keep track of them because it's important to know where they are. So I recommend that you draw lone pairs on your skeletal structures, but the rule says that you don't have to. Sometimes you'll see them drawn with and sometimes not. The only time you absolutely have to draw lone pairs is when you're specifically asked to in a problem, or if you're drawing a Lewis structure. You should always assume that lone pairs are necessary. All right, so on your activity, you have isopropyl alcohol and you have N-propyl alcohol. So these are 2 different chemicals that are very similar, but they're not the same thing because they have a different connectivity of the atoms. And the different connectivity is represented by 4 of these representations, but not 1 of them. So the molecular formula doesn't tell you anything about the connectivity, but the condensed structural formula, the Lewis structure, the skeletal structure, and the ball and stick model show you that this molecule has 3 carbons attached to each other, and the end carbon is attached to an oxygen. So if we compare isopropyl alcohol to N-propyl alcohol, what I'd like you to notice is that they have the same molecular formula. So they both have the same number of carbons, same number of hydrogens, same number of oxygens. The only difference between these molecules is the way that their atoms are connected. And these things are called structural isomers. So it's a kind of isomer that's called a structural isomer. So the molecular formulas are the same. But notice that in the ball and stick model, you can tell that in isopropyl alcohol, there's an oxygen connected to the second carbon. And in N-propyl alcohol, there's an oxygen connected to the end carbon here. So second carbon and end carbon. And then you can see those differences in the condensed structural formulas, if you compare them, in their Lewis structures, and in their skeletal structure. So once again, the skeletal structure means that there's a carbon here with 3 hydrogens, a carbon here with 2 hydrogens, and then in this case, a carbon with 2 hydrogens here that's connected to an OH group. All right, so what I'd like you to do now is pause the video and try to answer the questions on this page and on the following page. And then you can unpause the video, and there's a couple that I want to go over with you. Okay, 7 asks you to complete the table for isobutane and N-butane. So I'd like to make sure that we understand. Isobutane and N-butane have the same number of carbons and hydrogens. So they have the same molecular formula. And that means that they are probably isomers. And you can tell that they're definitely isomers if you notice that they have the same molecular formula and they have a different connectivity of the atoms. So notice that in N-butane, all of the carbon atoms are attached in a chain, so they're just 4 in a row. And then the hydrogens fill in basically where you need more bonds. And then in this isobutane, there's 3 carbons in a row and 1 carbon off of the middle carbon. So there's actually 1 carbon in the center with 3 carbons spoking out from the center. And then hydrogens all around to fill in where the carbons need for bonds. So there are a couple different ways you can do that. You can answer this question. And the answers I'm showing you here are not the only answers, but they're some of the correct answers. So if you were going to draw the skeletal structure, basically you could draw something like this. It doesn't matter which direction these things are pointing, as long as there's 1 carbon in the middle, or basically 3 lines that are intersecting at one point. That means that there's 1 carbon in the middle with 3 carbons spoking out from it, and then you assume that the hydrogens are all connected. For this one, it's just 4 carbons in a row. And so the way, you don't want to draw 4 straight lines that are like all in one big line, because you wouldn't be able to tell where the carbons were. And so what we do is we draw it as a zigzaggy line. And so there's a carbon here, and there's a carbon here at this corner, basically where this line segment and this line segment are intersecting. There's a carbon. So carbon, 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 carbon. And it doesn't matter how you start the zig. You can zag first or zig first. So I could have gone from the top down like that. Or I could even draw it vertically instead of horizontally. It doesn't matter. Or I could even draw it kind of in a U shape. As long as there are basically little corners and ends of the lines that give you 4 total carbons. And then you don't draw any of the hydrogens. For the condensed structures, there's several different ways that you could do the first one. The second one is pretty simple. You just, you draw a carbon with the 3 hydrogens attached, then the next carbon with the 2 hydrogens attached, then the next carbon with the 2 hydrogens attached, and then the next carbon with 3 hydrogens attached. So that's one way you can do it. And then for this one, there's several different ways. You could first just draw this carbon with the 3 hydrogens attached, this carbon with 1 hydrogen attached, and then this guy is kind of a branch or like a thing off to the side. And so we put this in parentheses to show that it's attached to the carbon behind it. So this carbon is attached to a hydrogen, and this whole CH3 group here, which we put in parentheses. And then it's also attached to this CH3 group. You can also draw this condensed structural formula with the carbon in the middle, starting with the carbon in the middle, and you could basically say this carbon is attached to a hydrogen and 3 of these CH3 groups. So that was 1, 2, 3. Or you can just say 3 CH3 groups attached to that center carbon with 1 hydrogen. So there's many different ways you can do these, and it doesn't really matter which way you're doing it as long as it's correct and following the rules. So if you have any specific questions about what you're doing, feel free to come and ask me about that when I get back into town. I also want to talk about number 9. So number 9 asks you to give the skeletal structure for 2 of these molecules shown. And so what you want to do when you're taking a condensed structural formula and making a skeletal structure is you basically just want to count the carbons that are going to be part of the chain. So you basically ignore everything that's in parentheses like this one. So I'm going to call these A, B, C, D, E, F, and G. So A, B, C, D, I skipped this one because it's not part of the main chain. So A, B, C, D, E, F, G. And then I would just say A, B, C, D, E, F, G. Oh, I'm missing one here. There should be a G here. So please make sure that doesn't throw you off. There should be an extra line here. And then I can see that this carbon here only has 1 hydrogen on it. So it would be connected to that carbon, it would be connected to that carbon, and there's only 1 hydrogen, and so it needs 1 more bond. And that 1 more bond is actually to this carbon. So then I draw that off of D, so A, B, C, D, and I draw that guy up. So I've tried to color code this to kind of show you, but please don't let that mistake that I made. There should be 1 extra little line off of this F to represent carbon G. So then this one over here, I did the same thing. I just basically lettered the main chain here, A, B, C, D, E, F, G, and then I just zigzagged A, B, C, D, E, F, G. So that's a total of 1, 2, 3, 4, 5, 6, 7 carbons that are represented by this pink line for the skeletal structure. And then Carbon B has one little guy off of it, so I just draw that. So that's represented CH3. And then carbon F has 3 carbons, so I represented this little, I label these with kind of a number symbol, but you don't need to do that. So basically you just want to make sure that F is connected to 1, 2, 3 carbons all in a row. And that's how you draw a skeletal structure. When you're drawing skeletal structures, if you're going to draw a substituent or something that's coming off of the main chain, like I did on B here, see how this is kind of like a little arrowhead pointing up? You want to draw your substituent in the same direction as the little arrowhead, so up. So if I was going to draw something on C, see how the little arrow thing, if I think about this angle as like an arrowhead, I would draw the substituent down. And so if you get in the habit of doing that, it'll help you out later on. So notice how I've put D as the substituent on D pointing up, B pointing up, and F is pointing up as well. Okay, and one more for this. I'd like to just talk about number 11 one more time. This is how you would draw a condensed structural formula from a skeletal structure. So for this one, again, there's a lot of different ways I could do this. I could start from here or I could start from here. So the first example here is starting from this carbon. So it's drawing 1 carbon with 1, 2, 3 CH3 groups on it, because each one of these carbons is attached to 3 hydrogens. So that's the carbon there, and then those are the 3 CH3 groups. And then a CH2 and a CH3. Or you could draw, there's different ways. So I'll let you try to figure out how these translate into this skeletal structure. Here's a different example. For this, you just basically start at one point and start drawing. So here's CH3, CH2, CH2, this one, C. This carbon's attached to 1 hydrogen because it's already got 3 bonds, so that's a CH. It's attached to this group here, and so I would represent basically CH and then attach to 2 CH3 groups, so CH, 2 CH3 groups. Okay, that whole thing is in parentheses, and then CH2, CH3. And then I'll let you figure out how that translates into this one. And over here, there's an example where you have a double bond. So it doesn't matter where you start here. You could start here, you could start here, you could start here if you wanted to. This one, I've actually started here at this end. So it's CH3, CH, and then this substituent here is CH2, CH3. And then I close the parentheses, and I already took care of this carbon. So then I go CH2. This carbon only has 1 hydrogen on it because it already has 3 bonds. It has 1, 2, 3 bonds to this carbon. So it has 3 bonds. That means it only has 1 hydrogen. So that's why I drew CH here for that guy. And then this is CH2 because this carbon has 2 bonds. And that means, sorry, it has 2 bonds to carbon, this carbon. So this carbon has 2 bonds to this carbon, and that means it needs to have 2 hydrogens on it. So that's why this is CH2. Sometimes you'll see a little double bond symbol in here, but that's technically not a pure condensed structural formula. So if you have multiple bonds, you basically represent it by the number of hydrogens, because here this carbon is only attached to this carbon and this hydrogen, and so it needs 1 more bond, and that means that it must be attached 1 more time to this carbon here. So you can use logic to figure out, basically understand how one of these things translates into the other. Okay. Any questions? I will be happy to try to answer them if you post them in the comments, or I will answer them as soon as I am in South Bend and available for you to talk to. So I will let you know by email when I'll be back. Okay, now let's talk about functional groups. Functional groups are one of the most important things that we're going to learn to understand how chemistry happens. So a functional group is basically a part of a chemical that has a certain reactivity. So we're going to learn about these functional groups. And for now, I just want you to become familiar with them. This is the kind of information that you might want to have on your cheat sheet. So I have my functional groups in this slide organized a little bit differently than they are in your textbook. And I like to organize them this way because it organizes them by type. So the first things I'm going to talk about are hydrocarbons. So these are things that are made of just hydrogen and carbon. And alkanes are just regular old hydrocarbons with just carbon-hydrogen bond. There's no double bonds. There's nothing fancy. And this is a family name. It's not technically a functional group, so don't call it a functional group. But it's worth mentioning because it is one of the main things that we'll be talking about this semester. Okay, so now on to the real functional groups. Whenever you see a carbon-carbon double bond, it's an alkene. So notice the ending here is different than this ending. So when it has a double bond, there's an ENE, alkene. If there's a triple bond, and this is not a very good representation, but these carbons should have a triple bond between them, it's called an alkyne. So anytime you see a triple bond between two carbons, it's going to be called an alkyne. Aromatic is anything where you have a ring of carbons and there's double and single bonds that alternate around the ring. So these are the most common ones that you'll see. Okay, so those are the hydrocarbons. Those are the ones that are carbon and hydrogen, and then, there's this weird one here, but it's not technically a hydrocarbon. So then alcohols are anything with an OH group. So anytime you see an OH group like this, anywhere on a molecule, it's an alcohol. And the alcohols are categorized by the carbon that the alcohol part, so the OH group, is attached to a carbon, and they're categorized based on how many carbons that carbon is attached to. So I've highlighted that carbon in red. Okay, so if the carbon, so this is representing that the carbon here is attached to something else. It's another carbon, and there might be a bigger part of the molecule. So that's kind of my shorthand that this is attached to another carbon. When the carbon of the alcohol is attached to one other carbon, it's called a primary alcohol, and you represent it like this, 1 degree. So it's primary alcohol. When the carbon attached to the alcohol is attached to 2 other carbons, so this is one and this is the other, then it's a secondary alcohol. And when that carbon is attached to 3 other things, it's a tertiary alcohol, or 3. And then a special case of when an alcohol is attached to an aromatic group is called a phenol. So even though this is an alcohol and this is an aromatic group, when they're together, they're called something else. It's kind of like the phenol trumps the other two. So this is a phenol. And then the thiols are just basically the same as alcohols, but with sulfur. You'll see ethers where oxygen is attached between 2 carbons. A peroxide is where 2 oxygens are bound together and they're attached to 2 other things. It doesn't actually need to be a carbon. So know a peroxide, know what an ether looks like. A thioether is just the same thing with sulfur. A disulfide is just the same as a peroxide, but with sulfur. And remember that if you look at the periodic table, oxygen and sulfur are right underneath of each other, so they have the same types of structures. Amines are chemical functional groups that have nitrogen in them. And nitrogen, so now notice you have the same type of classification system as you did with the alcohols and the thiols, but it's different for amines. So for an amine, they're classified by the number of carbons directly attached to the nitrogen itself. So this nitrogen here is attached to one carbon, so it's a primary amine. This nitrogen is attached to 2 carbons, so it's a secondary amine. This nitrogen is attached to 3 carbons, so it's a tertiary amine. And this nitrogen would be attached to 4 things, 4 carbons in particular, and it's a quaternary amine. And notice because nitrogen doesn't usually have 4 bonds, there's a positive charge on the nitrogen. You can also have these things that are protonated. Basically, that means the nitrogen has 4 bonds, but still they're classified by the number of carbons attached to the nitrogen. So here's a primary amine. The nitrogen is attached to 1 carbon. Here's a protonated, basically a proton. It has an extra hydrogen. Proton and hydrogen are the same thing. It's protonated amine. It's still attached to one carbon, so it's a primary protonated amine. This is a secondary protonated amine and a tertiary protonated amine. And then we have the carbonyls. So carbonyls are anything that have a carbon double bonded to oxygen. So notice there's a carbon double bonded to oxygen in all of these things. When you have a carbon double bonded to oxygen and it's attached to a hydrogen, it's called an aldehyde. When the carbon is attached to two other carbons, it's a ketone. When the carbon's attached to an alcohol, so now this is a new functional group that basically it's kind of like two functional groups together, right? An alcohol and a carbonyl. So when those things are attached, they're called a carboxylic acid. And if the hydrogen is not there, you have a negative charge on oxygen, it's called a carboxylate. An ester is where it's a carbon attached to, basically, it's like a carbonyl and an ether group. So the carbon is attached to an oxygen attached to another carbon. That's an ether. And then an amide is basically like an amine attached to a carbonyl. So you can have a primary amide, a secondary amide, and a tertiary amide. These are the functional groups that you should get familiar with. Just put them on your cheat sheet and use your cheat sheet as you're going through your problems in your textbook. And for the rest of the semester, you'll have that. Okay. How about we practice? What I'd like you to do is find this problem on your activity and practice identifying the functional groups. Circle them and name them in these three structures. Pause the video now and do this activity, and then I'll give you the answer. Okay. In aspirin, we have three functional groups. So we have an aromatic group here. We have a carbonyl. This is a carbon double bonded to oxygen attached to an oxygen carbon. So this is a special carbonyl called an ester. And here again, we have a special carbonyl, and this one's called a carboxylic acid. So these are the three functional groups that you circled. You should not circle this individually, like this is not an alcohol. This is a more complicated functional group called a carboxylic acid. And this is not an ether here, it's a more complicated functional group called an ester. For alanine, there are two functional groups. You have a primary protonated amine, so that's a nitrogen with a positive charge, and it's attached to only one carbon, this carbon. And here we have a carboxylate, so this is basically the same as a carboxylic acid, except without the hydrogen, and it has a negative charge on the oxygen. Over here in acetaminophen, there are two functional groups. One is a phenol. It's this whole thing together, including the alcohol and the aromatic ring. So that's a higher order or more complicated functional group called the phenol. And here we have an amide, which is a carbonyl attached to a nitrogen. So that's an amide. Don't circle just the little parts of these, right? When they're more complicated functional groups, you just circle the whole thing. And in this case, it's an amide and a phenol, rather than an alcohol, an aromatic group, an amine, and a carbonyl. There's another question like this in the check for understanding. So make sure you try that one and check your answers against the answer key to make sure you understand this information. There's only one thing I want to mention before I go, and that is for question number 2 on this part and on this activity, you'll need to peek ahead to the next activity, and you'll need to see that ethane is a 2-carbon molecule. So you need to know that, and we're going to put that together basically with some new information in number 2, because they're asking you for the structure for ethyl alcohol. And ethyl alcohol is just an alcohol functional group on the ethane molecule. So these are names that we'll learn in the next activity. But ethyl alcohol is basically just this CH3, but then it's CH2 so that the carbon can be attached to an alcohol, or you could call it, basically you could reverse the order here. But that's the skeletal structure, and that is one representation for the condensed structural formula for ethyl alcohol. All right, hopefully I'll be back tomorrow, and I'll see you in class on Tuesday. Have a good day.